2, 1. All right. Welcome to topic 5, continuity, for our Math 492 here in fall 2021. And what is, I think I said in the last video, what is hopefully our last online video. But yeah, this will definitely be. Fingers crossed. Alright, so what are we talking about today? So we are going to continue our path down topology for the next few weeks here. And what we are now going to do is get to the topic of continuity, what I think is the central topic of topology. So like I was saying, the definition of a topology, which we now know, is a very technical definition about a set having a collection of subsets with nice properties, which of course we saw this with the real numbers, but as we've now demonstrated, you can kind of cook up various topologies of various styles, and we'll get more into that next week when we talk about metric spaces, which are a very specific kind of topology. But before we get there, I want to now talk about the core idea, which is continuity. Right, so while we now have officially what a topology is defined as, I know it's very set theoretic, the way it's defined, we can now talk about continuity, which is, in my opinion, what topology is all about. Topology, to me, is the study of continuity. It's the study of continuous things. So, how do you define continuous in a topological space? So remember, when we define continuous way back in Calc 1, it's a property that happens at a point, right? A function is continuous at A if the function is defined at the point, the limit exists, and those two quantities are equal. And as we discussed, that's kind of a bit of a lie. If the point A is a limit point of the set, then yeah, that's true. But if it's an isolated point, then it's just automatically continuous there, so we don't care. All right, but let's now talk, how do you topologically define it? So we need to define continuous at a point, and the way to define that is as follows. So if you have a function from a topological space X to a topological space Y, f is continuous at the point A if any open neighborhood of f of A, we can find an open neighborhood U so that the image of the open neighborhood U of X is contained in the open neighborhood V of F of A. And that should be a open neighborhood of A, not X. Let me fix that. And for the magic of LaTeX, it's fixed. Beautiful. Yeah, so hopefully this does seem right? Because think of the epsilon delta definition for continuity. Given an epsilon, there is a delta, so that anything within delta is within epsilon. That's exactly what this is saying. So this is the right definition, right? It does match up with our previous one, and in fact, as we will now prove, it does line up with what we proved for any continuous function on the real line, that the inverse image of open sets is open. So, as we just noted, topology is something that's defined at a point. So if you are continuous at every point in your domain, we say that you're a continuous function. And as we will now prove, it turns out that continuity is equivalent to 5 very useful facts. And here we see at fact number 2, our thing that we prove for the real numbers. The inverse image of open sets is open. Beautiful. All right, so here we go. This is a very powerful theorem, giving us various characterizations of continuity in terms of not only just open sets, but also in terms of closed sets. Right, and as we noted, closed sets are the complements for open sets. They are the ones that come along as well. And note that open and closed, while the words may be antagonists in topology, they're friends. It's possible to be not open and not closed. It's also possible to be both, as we've already noted. Alright, so we are now going to prove that continuity here lines up with what we proved for the reals. The inverse image of open sets is open. Beautiful. Alright, so let's note here, I've got 5 things that I'm claiming are equivalent. So whenever I have a list of the following are equivalent, I always do 0.1 implies 0.2, 0.2 implies 0.3, 0.3 implies 0.4, 0.4 implies 0.5, and 0.5 implies 0.1, thus completing the loop, and thus everything is nice and equivalent. Sometimes you'll get textbooks where they're like, the following is equivalent, and we're going to prove 1 and 5 are equivalent, and then we'll prove that 2 implies 4, and then we'll apply that 4 and 3 are equivalent, and then we'll prove that 4 implies 1, and therefore everything is equivalent. I hate when books do that. I had a professor in my topology class, actually, where there was a big theorem and had like 8 parts, and he drew a graph, and he was like, "Okay, I've got these 8 things," and then he drew all the lines. He's like, "Here's what I'm going to prove." It sucked. But whenever I do it, I always do 1 implies 2 to just go down the list, and then close the loop at the end. Then Bruce Willis comes in, and things are good. All right, so that's what we're going to do. All right, so let's start off. We'll assume continuity, and then we'll show that inverse image of open sets is open. All right, and if you pay really close attention to this, this is essentially going to be the same proof that we did for the real valued case, but a hell of a lot easier because we're not going to have to get hung up on a bunch of epsilon delta garbage. All right, so suppose we're continuous. Take an open subset and let X be an element of the inverse image of U. I'm trying to prove this is open. So what do I want to do? I want to show that there is an open neighborhood of X that is contained in this set. All right, now what does it mean to be in the inverse image? That means that f of X lives in U. All right, and hey, this is an open neighborhood of f of X. Since f is assumed continuous, I can then find an open neighborhood V of X so that the image of V is contained in U. Right, so again, given an epsilon, there is a delta. That's effectively what we're mimicking. All right, and then now what do I do here? Well, apply F inverse. Indeed, if I apply F inverse here, note that I will get the following. So hopefully from your set theory days in Math 201, you remember that if I take a set, do its image, and do its inverse image, that doesn't necessarily equal V, but anything in V is obviously in the set. Pick an element in V, its image lands in f of V, so its inverse image, yeah, it lives in there, definitely. No, you don't necessarily have equality here, but you do have subset. X lives in V, which lives in this, and since this is a subset of that, inverse image respects subset, so now we've got X lives in F inverse of U. So what do we now have? Actually, I don't need that X is in there. I already know that. That's kind of redundant. What I really need is that V is contained in F inverse of U. Right, V is an open neighborhood of X, so we've now demonstrated that every element of the set has an open neighborhood that is contained within the inverse image of U, so it's got to be that the set is open. And there we go. Inverse image of open sets is open. Continuity. There you go. Beautiful. Right, and like I said, if you really look at this, this is exactly the proof we did, the epsilon delta proof that we did. Right? Given an epsilon, there is a delta. That's what these are mimicking. But note, we're not getting hung up on anything about the real numbers or absolute values or any of that junk. Just purely how do sets and functions work. Boom. So here is kind of our first example, and we're going to see a lot more of this later on, of topological arguments massively simplifying the analogous arguments for more concrete mathematical objects. And one of the reasons topology has caught on, and especially in other branches of math, where topological arguments tend to be a lot cleaner because they only involve the sets. So they only involve sets and subsets and functions usually. And those just purely, right, those just literally just moving symbols, so you're not getting hung up on the minutia of what's going on. So later on we are going to prove the intermediate value theorem and the extreme value theorem, and we're going to see that the topological proofs are like one line. They're like virtually nothing. Which is really nice in comparison to the normal proofs that you either will see in Math 414 or the proofs you saw in Math 414. Which are highly reliant on least super bound property nonsense. But the topological arguments are just going to be, yeah, topology is nice, so we're done. So here we kind of get our first glimpse of it. Cool. All right, well, that's the first implication. We've got 5 more to do, so let's get going. All right. So point 2 implies point 3. Let's remind ourselves. Point 3 is saying that given an element and an open neighborhood of f of x, then the inverse image of that set is an open neighborhood of X. So note that the normal definition of continuity gives us some open neighborhood. It doesn't tell us exactly what it is, but here we're seeing that it explicitly can be chosen to be the inverse image of the original open neighborhood. All right, cool. So it's a kind of an upgrade from the normal definition where given an open neighborhood of the output, there is an open neighborhood in the domain, but we don't know what it necessarily is. This is telling me that I can always take it to be the inverse image of U. So that's nice. So let's prove that. All right, well, so we'll suppose, right, we're supposing point 2, and we're going to prove point 3. Suppose that the inverse image of any open set remains open. Pick a point X and take an open neighborhood of it. Well, by assumption, the inverse image of the set is open, and X lives in there, so boom, there's our open neighborhood. Done. Nice. So point 2 implies point 3 is definitely the easiest of the implications we're going to see, because it's literally just, oh yeah, the hypothesis just gives you this. Alright, however, point 3 implies point 4 is going to be the meaty one here. So we will now prove that this condition ensures that given any subset of X, the image of its closure is contained in the closure of its image. Right, so again, the mathematician's favorite snow clone, the X of the Y is the Y of the X. So in our case, the image of the closure is contained in the closure of the image. And I should be a little bit more. So one thing with closure that's worth noting, and this is a habit that a lot of mathematicians have, is not using parentheses with the closure. It's like, you know what I'm talking about, CL of this. I should be a little more careful with that. Also worth noting with closure, another notation that people use for closure is the following, and I utterly hate this, which is that notation. You put an overline on it. I hate that because in complex analysis, of course, that means conjugation. So I'd be talking about the collection of elements that are conjugates of the. So I don't like that. I like CL for closure. But some people do a bar over the set for closure. That is kind of standard. But I'm more fan of just saying CL, which is also standard. All right, okay, so 3 implies 4 is going to be the meatiest one, because note, we're going from open sets to closed sets, so we're making the jump. But remember, how is closure defined? Well, there's a couple of ways of thinking of closure. It's, of course, the smallest closed set that contains E. It is also the collection of points so that any open neighborhood meets E. And I'm assuming open neighborhoods are behaving, so that's how we're going to make the connection. Okay, so let's get to it. All right, so suppose that we know that for every element X and any open neighborhood of the output, the inverse image is an open neighborhood of the input. Okay, so again, just kind of beefing up the definition of continuous functions, allowing us to go, well, okay, so given any open neighborhood of an output, there's an open neighborhood of the input. So given an epsilon, there's a delta. This is saying that the delta can be kind of chosen efficiently in a way. Okay, so what do I want to prove? I want to prove that the image of the closure is contained in the closure of the image. So take a set and take an element in the image. I want to show that Y is in the closure of the image. All right, well, since I'm in the image of the closure, that means Y lines up with f of X for some X in the closure. I need to show that Y is in the closure of the image, so I'm going to now take any open neighborhood of Y. Note that Y is equal to f of X, so our hypothesis here, and note I'm using it. If I didn't use it, that'd be weird. Our assumptions imply that f inverse of U is an open neighborhood of X. Okay, X, though, remember, lives in the closure, which means I can find something in this intersection. Right, this is an open neighborhood of X, and X is in the closure, so this intersection is not empty. Now, since Z is in the set, that means Z is in this set here, right? So f of Z must be in Z, and since Z is in E, f of Z is in f of E. Now, this means that U intersect FE is always non-empty. And that's true for any open neighborhood you choose of Y. And I like that parentheses missing there. Man, these slides are a little jank. So yeah, what does that mean? That means then that Y must be in the closure of the image, because this intersection is always non-empty, and that's what it means to be in the closure. Cool, so this was the most involved one out of the 6 implications we have to do, right? We have 5 points, so there's simply 6 implications. Yeah, 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, and not 5 implies 1. Yeah, there's 5. What am I smoking? I can count. I don't know how to count. Right, 1, 2, 3, 4, 5. Yeah, I know what I'm talking about. All right, so we have 2 more to go. All right, so this was the most involved one. This was definitely the most difficult one out of the 3, but hopefully not too bad. And again, note the style of argumentation here. Note how these proofs are going. It's just purely how sets work. It's literally just built off of the behaviors of sets and images of functions. It's just we're not caring about anything else. We're just focusing on sets, the building block of mathematics. Right? So these to me especially, these proofs are just wonderful. All right, and yeah, here we go again with the freaking parenthesis here. Jeez, swear to God. All right, so we will now prove that if I know the image of the closure is contained in the closure of the image, then the inverse image of any closed set is closed. So take a closed set, and then we will let E be its inverse image. I am going to prove that E must be a closed set, and remember that you're closed precisely if you're equal to your closure. And hey, I'm assuming something about closure, so I'm probably going to prove that. All right, so E is the inverse image of that. Note that if you now do the image, you'll have the image of E. The image of the inverse image is always contained in the original set. F, by hypothesis, is closed, so that means the closure of the image is contained in F, right? Because the closure is the smallest closed subset contained in the original set. Now, our hypothesis tells me that the image of the closure is contained in the closure of the image. So the closure of E is contained in the inverse image of the image. This, I proved, is a subset of F, so I get this. The inverse image of F is what E was equal to, and E is always contained in its closure. Hey, closure of E, subset of E. Closure of E is equal to E, so that means the inverse image of F, which is what E was defined to be, is indeed closed. And the proof is over. Well, this implication is over. Beautiful, there we go. So we have now proven that the inverse image of any closed set is closed. And so the final thing we need to do now is prove continuity. So we need to prove that for every element x in the domain, and any open neighborhood containing f of x, I can find an open neighborhood so that the image of f of u is contained within V. All right, so suppose that f inverse of f is closed for any closed subset of y. All right, take an element x and an open neighborhood of the output. Note that the complement of this open neighborhood then is a closed set. So the inverse image of this would then be closed. And now what is the inverse image of this equal to? So the inverse image of a complement is the complement of the inverse images. The inverse image of the codomain of a function is going to be the entire domain. So, hey, the inverse image of y complemented with V is a closed set, which means this is closed, which by definition means that f inverse of V is open. So set U to be f inverse of V. That's an open neighborhood of x by definition, right? Since f of x lives in V, that means x lives in f inverse of V. And if I take the image of U, that is contained in, and is equal to, not contained in. Yeah, these were put together, again, kind of as quickly as I could. This is equal to the image of f inverse of V, which, as we've already justified, is a subset of V. And there we go. So given any open neighborhood of an output, I can find an open neighborhood of the input so that the image remains in V. So f is continuous at x, and x was chosen arbitrarily, so f must be a continuous function. Beautiful. All right, so now that we have this big old theorem telling us when functions are nice and continuous, let's start talking about continuous functions a little bit more. Let's prove some theorems. Okay, so there's a few things that we can now prove, one of which a student will do, but one that I want to do to give you a flavor of kind of how these proofs go now is that if you have a continuous function and you take any subset of x, we can talk about the restriction of the function f to that set. If you take a continuous function and restrict its domain, you will remain continuous. And this is super easy to prove now. Take an open subset of y, the inverse image of U is continuous, by hypothesis. Now, if I look at the restrictions inverse image of U, well, that will just be the inverse image of U intersected with A. This is an open set in X, so when I intersect it with A, I get something that's open in the relative topology on A. So the inverse image of any open set is open in A, so the restriction is continuous. Beautiful. Right, we talked about this a little bit with the reals, where we were looking at that example of f of x where it's equal to x from 0 to 1, and then at 2 it's 2, which is like, this is the normal continuous function y equals x, but you're just ignoring some of the inputs. So that we would want that to remain continuous, which of course led us to having to circumvent the usual definition of limits. All right, but beautiful. So there we go. And again, note the proofs here. They're kind of really beautiful. They're kind of really nice. All right. Okay, so let's keep going. So something that... Sorry for all the noise I'm making. I'm in my office recording this, and I got a squeaky chair and a loud desk. So for all the ambient noise here, yeah, the ambiance that I'm giving you. All right. So something that we care a lot about in topology is the idea of a homeomorphism. And the idea here is, given two topological spaces, you want to identify if they're the same thing. And it turns out the way to do that is through this object called a homeomorphism. So note it's a bijection, meaning that x and y have the same elements, same number of elements on cardinality, right? Everything in x can be uniquely put into a one-to-one correspondence with everything in y. And it's a homeomorphism, so f is continuous and f inverse is continuous. So two topological spaces are identical if you can find a homeomorphism between them. And detecting a homeomorphism is pretty easy because all you need to do is the following. First, you need to know your functions of bijection. Then, in order to be a homeomorphism, well, you don't need to know if inverse is continuous. You just need to know that f is behaving well. Specifically, that f is continuous and that the image of any open set is open. So remember, continuity means inverse image of open set is open. Homeomorphism, the extra condition of the image of every open set is open. Of course, under the assumption of bijection. So let's prove this, and it turns out there's not really too much to do here in the proof. So suppose that you do have a homeomorphism. Okay, that means f and f inverse are continuous. So we have f is continuous. Now it's only to show that the image of any open set remains open. So take an open set. F inverse, by hypothesis, is continuous, and as it turns out, the image of U under F is the same thing as the inverse image of F inverse of U. Now, this notation right here can get a little trippy, because it's kind of looking like, oh, the inverse of the inverse is F, so we're good. But not really, because here, this is the image of U under F, but this is the inverse image of U under F inverse. So it is kind of a overload of notation that gets a little bit messed up, which is why some people, when they talk about inverse image, the notation that they'll use is actually this. So instead of having an inverse here, they'll do a left arrow to be like you're pulling it back to avoid kind of a notational faux pas of having f inverse to the inverse and it being not clear, but I never really got into that. I've only seen that in very select, like some old-ass textbooks from like the 60s and 70s will do that, but this is pretty standard now where it's understood that you know what we're talking about, so, but yeah. All right, but anyway, yeah, so we now have that if you have a homeomorphism, then f is continuous and the image of any open set is open. So not only do we know the inverse image of open sets are open, we also know that the image of open sets remains open. So it is worth noting you can study this property on its own. So a function is actually said to be open if the image of any open set is open. So you call the function open if it does that. Open functions, they're also called open mappings, are very useful. In fact, there's a big famous theorem called the open mapping theorem. So check that out if you're interested. I don't think we're going to have the time to get into that. That I don't think it's very far afield. But if you're interested, check it out. All right. So, note that we're proving an if and only if. So I got the if. Now let me get the only if. So suppose we have continuity and that the image of any open set is open. Well, given an open set, that means the inverse image of f inverse of u is open. So f inverse is continuous, and that's what it means to be a homeomorphism. So, yeah, not the most exciting proof, but a proof that lets us deal with homeomorphism without having to figure out what the hell f inverse is. Because in some cases, while it's nice that a function's bijective, sometimes a formula for its actual inverse eludes us. So having this characterization without having to actually work with f inverse is nice. All right, beautiful. All right, so let's get a one more proof to get, again, we're not going to go through every single possible fact about continuous functions, but it is worth proving a couple of things about them so we get a little flavor. So something that we know from calculus is that the sum of two continuous functions is continuous. So let's prove that. We can now prove this, right? The real numbers have their usual topology, and unless otherwise stated, the real numbers are always assumed to have their usual topology. A little later on, we'll talk about other topologies you can put on the reals. A very famous one is something called the Sorgenfrey topology, but we'll get to that. There you get some really goofball topological examples. But anyway. So we'll prove that the sum of two continuous functions remains continuous, something that, we know from calculus. All right, so how are we going to prove this? Well, it's actually pretty easy to prove this, but it does involve some epsilons, unfortunately. But that's okay. Okay, so take an open subset of the reals. I'm going to prove that the inverse image of f plus g is in fact open. All right, so take an element of that set. I'm going to find an open neighborhood that contains x and is contained in this set. All right, so given an x in here, we then know that f of x plus g of x lives in u. And that's what this is saying. What does it mean to be open in the reals? That means I can find an epsilon, so that if I subtract this by epsilon and add epsilon to it, I get a interval that is a subset of u. Now, since f and g are continuous, and this is an open neighborhood of f of x, and this is an open neighborhood of g of x, that means this inverse image is an open neighborhood of x, and this inverse image is an open neighborhood of x. So note, I'm using the theorem that we started the lecture off with. Okay. So note, while x is not the reals, I am still kind of doing an epsilon delta argument. Right, given an epsilon, these things are now taking the place of my delta. And hopefully, as you'll see, it makes the proof a little bit easier. All right, so I need to find an open neighborhood that contains x and is a subset of this, which would guarantee that this is an open set. And so the inverse image is open. So the v I'm going to take is the intersection of those two things. So note that by construction, this is an open neighborhood of x, because this is an open neighborhood, and so is this. All right, I claim that v is contained in here, which then ensures that the inverse image of this set is open, and life is good. Okay. All right. Well, I need to prove that v is contained in the set, so take an element that lives in v. I need to show that f of y plus g of y actually lives in u. All right, well, f of y is in this set. Since y is in v, it means it's in this, which means f of y lives in that set. Similarly for g. And then if you look at f of x plus g of x minus f of y plus g of y, all right, by the triangle inequality, that splits up like this. This here, since f of y lives in here, must be less than epsilon over 2. Here, since g of y lives in here, that means this must be less than epsilon over 2. And hey, add them together, you get epsilon. So that means f of y plus g of y must live in this set, which is a subset of u. So f plus g of y is in u, so y is in the inverse image, And there we go. This open neighborhood of X is contained in the set, guaranteeing that this is an open set, so the inverse image of open sets is open, thus F plus G is nice and continuous. So there we go. So, yeah. Beautiful. So, proving the sum of two continuous functions remains continuous. There you go. Now, naturally, of course, you're like, hey, I got the sum. Let me get the product. I'm not going to do that proof, but we are going to have somebody prove something related to it. Okay, so a student will perform the following. So note, when I see you in person next week, we will have 3, count them, 3 presentations. It'll be very exciting. All right, so what is a student going to do? Okay, so the first thing is that hopefully you remember the composition of two continuous functions remains continuous. So we'll start off with that. Just look at an inverse image of an open set, and you'll be good. All right, next up. So something that hopefully creeped into your mind when we defined homeomorphism was the following. Hey, the assumption was that both F and F inverse were continuous. Is it possible for F to be continuous and F inverse to not be continuous? And the answer is yes. So take this function here, prove that this is both bijective and continuous, and then show that its inverse fails to be continuous. So check that out. Somebody will prove this. And then finally, the last thing somebody will prove is a pretty neat fact for real-valued continuous functions. Take any point in the domain. It turns out that you can then find an open neighborhood in the domain where all of the outputs are bounded. So that's probably kind of interesting. So it's not exactly the extreme value theorem, which says that every continuous function on a closed bounded interval is bounded, but it does give you some open neighborhoods and some bounds. So it's kind of neat. And the hint here is that you start off with this particular open neighborhood of F. So it turns out you actually need to prove this first before you prove that the product of any two continuous functions is continuous. So it's actually a little bit of work to prove that F times G is actually continuous. You need to use this fact in the proof. I do not know of a proof that does not use this. Yeah, so somebody will prove that. I was thinking of making somebody prove that F times G is continuous, but I was like, no, that's way too difficult. Actually, I'm lying a little bit. Another way of proving that the product of two continuous functions is continuous is to prove first that squaring a function doesn't ruin its continuity, but that's a little tricky. That proof also requires some algebraic trickery, so we're not going to do that one. Like I said, we're not going to prove the product. If you're interested, this is the first step. But yeah, so that's what we will have a student do. So, all right, that is it for today. So, see you in person next Monday. And we're going to have 3 student presentations. It's going to be a good old time. All right, see you next time.